Take a rope, tangle it up, and then fasten the two ends together. You've formed what mathematicians call a knot. Technically, we should imagine this rope has no width, so the knot is a one-dimensional object. Without doing any cutting or passing the rope through itself, this knot can be untangled to look like a circle, otherwise known as the unknot.
This is another knot. Unlike the last one, I'm not able to easily untie it. But how could I know for sure that untying it is impossible? I could mess around with it for hours and never get it untied, but that would only be evidence, not proof. Is there a way for me to prove once and for all that untying it is impossible?
We consider two knots to be the same if one can be transformed to look exactly like the other without cutting the rope. Thus, the question, can we untie this knot, is the same as the question, is this knot the unknot? This is a specific instance of the much more general question, are any two given knots the same? So our real goal is finding some way to prove that two given knots are not the same. To generalize the problem further, we'll introduce the concept of a link. A link is basically the same as a knot, except you can use more than one rope. Take any number of ropes, tangle them up as much as you like, and then fasten the free ends together until there's no more free ends. The result is called a link. Two links are the same if one can be transformed to look exactly like the other without cutting any of the ropes. The question we'll focus on in this video is, how can we prove that two given links are distinct?
This is a hard problem. There are a continuum of decisions one can make in how to deform a piece of rope. I could cross this piece over here, twist this end, deform this and slide this part through, and infinitely many other things I could do to try and make this link look exactly like the other. These changes are called ambient isotopies of the link. I could be sitting here for 10 days straight trying different ambient isotopies before I finally get it. A proof that the two links are different somehow has to rule out all infinitely many possibilities. It sounds like a formidable task, but there's a common strategy that's useful in these situations. The idea is to construct an invariant, a value you can compute from a picture of a link that doesn't change no matter what ambient isotopy is performed. If we're able to find an invariant that's easy to compute, and the two links in question are assigned different values under the invariant, then they must be different. For instance, there's a very simple invariant associated with a link called the number of components. That's just the number of distinct ropes used. This link has two components, and this link has one component. No ambient isotopy can change the number of components, so the links are certainly distinct. However, this invariant isn't particularly powerful, because there are lots of different links with the same number of components, and this invariant can't distinguish them. In particular, if we want to be able to distinguish two knots, which are just links with one component, we're going to need a stronger invariant.
There's a continuum of different ambient isotopies that can be performed on a link, and whatever new invariant we devise must be unchanged under all of them. Luckily for us, most of these isotopies are very similar. The result of this one looks more or less the same as the result of this one, which looks more or less the same as the result of this one. However, these two look more distinguishable, particularly because the pattern of rope crossings is different. In other words, in order to make one of these pictures look like the other, you have to slide the rope over or under itself. Two pictures that can be transformed into each other without changing the pattern of crossings are visually similar, and such a transformation has a name. It's called a planar isotopy, to emphasize the fact that the changes to the picture are happening in the plane rather than in the ambient three-dimensional space, which tracks the crossing information. All planar isotopies are ambient isotopies, but not vice versa. If we cooked up a quantity associated to a picture of a link that's computed solely from the link's pattern of crossings, then that quantity would automatically be invariant under planar isotopies. That's because two pictures that differ only by a planar isotopy, like these two, have the same pattern of crossings, and thus the quantity associated to each of them would be computed in the same way. So whatever invariant we develop, we'd like to be able to compute it from the link's crossing pattern.
Here's an example of a simple quantity called the linking number. It won't be able to distinguish two different knots, but it does fit our criteria of a number easily computable solely from the link's pattern of crossings. Take a picture of a link and assign an orientation to each component. That's just a consistent choice of direction along each rope, which we mark with arrows. To compute the linking number, take a close look at each crossing. If the overstrand and understrand are both part of the same component, write a 0 next to the crossing. Otherwise, consider what happens when the overstrand is rotated counterclockwise to be parallel with the understrand. If the arrows point in the same direction, write a 1 next to the crossing. On the other hand, if the arrows point in opposite directions, write a -1. Do this for every crossing, then add all the numbers together and divide by 2. You've computed the linking number for this oriented link. Although it's not immediately obvious, the linking number is an oriented link invariant, meaning that as long as you don't change the orientation of the components, any ambient isotopy of the link won't change the linking number.
This is quite a useful result. It tells me that this link, called the Hopf link, can never become this link, called the unlink, since the Hopf link has a linking number 1 or -1 depending on the chosen orientation, whereas the unlink always has linking number 0. If the two links were the same, there would be a choice of orientations for each that assigns them the same linking number. We skipped the proof that the linking number is actually unchanged under ambient isotopy. We'll come back to that later. But it should at least be clear that the linking number is unchanged under planar isotopy, because it's computed solely from the pattern of crossings, and any two link pictures related by planar isotopy have the same pattern of crossings. Unfortunately, the linking number of a knot is always 0, since the overstrand and understrand of every crossing are part of the same component. Thus, we can't distinguish two knots by their linking numbers.
There's a slight issue with how he presented the linking number, which you might have noticed. We assumed that every crossing was very simple. One rope, called the overstrand, passing over another rope, called the understrand, at a single point. This assumption was necessary in order to cleanly define the linking number, but in general, the crossings in an arbitrary picture of a link might not be so straightforward. For instance, one strand could touch another strand at a single point, like this, with either a cusp or a point of tangency. Or 3 or more ropes might cross on top of each other. Or 2 rope sections might be parallel and stacked on top of each other. In these scenarios, it's not exactly clear what counts as a crossing, what the overstrand and understrand are, and how to compute the linking number. To clearly define the linking number, we need to resolve these issues by ensuring that every crossing in the picture is simple. In fact, to clearly define any sort of invariant in terms of crossings, we need to ensure each crossing is simple. We'll do that by taking a link with problematic crossings and slightly adjusting it so that all the crossings become simple. First, to fix the situation with the cusp, we need to ensure that the path of the rope is differentiable. Smooth the rope out so there are no sharp points. We also need to make sure that there aren't any sections of the rope that are directly vertical, since when viewed from above, a vertical bit of rope can look like a cusp. Next, to avoid this situation with the point of tangency, we can just move the rope a tiny bit so that there's no intersection or there are 2 different intersections. This ensures that whenever a crossing occurs, if we look at the tangent vectors of the 2 strands, they aren't parallel. Finally, to avoid 3 or more ropes crossing at a single point, we just shift each one slightly so that we end up with a bunch of crossings with only 2 strands involved. These 3 conditions imply that at every crossing, there is a single overstrand and a single understrand, and the tangent vectors of these 2 strands are not parallel, so they form a simple crossing. A picture of a link that satisfies these conditions is called a generic link diagram, and we can easily compute the linking number of an oriented link from such a diagram.
In summary, we've seen that if we want to devise a new link invariant, we need a quantity that's invariant under ambient isotopy. Such a quantity certainly must be invariant under planar isotopy, so we want to define it solely in terms of the link's pattern of crossings. To do this, we need simple crossings, which occur when we're working with a generic link diagram. But being invariant under planar isotopy isn't enough. We need a quantity that's invariant under all ambient isotopies, which can change the pattern of crossings. Thus, we should consider what kinds of changes to the crossing pattern can occur when an ambient isotopy is performed. It might seem complicated, but it turns out that all the crossing changes that can occur can be broken down into a combination of 3 simple kinds of changes called Reidemeister moves. To see where the Reidemeister moves come from, I'll start moving this link around. Notice that most of the time, the crossing pattern isn't changing. In other words, I'm applying a planar isotopy. However, there are certain isolated instances where new crossings emerge, old crossings are eliminated, or the pattern of crossings changes in some other way. For instance, when I give this strand a twist, a new crossing is generated at this single instant. Or, if I slide this strand over here, 2 crossings are eliminated right now. I could also move a strand like this, causing the pattern of crossings along this rope to go from under-over to over-under, and the change occurs exactly at this moment. Now here's the critical observation. Changes to the crossing pattern only occur when the link diagram isn't generic. If we alter the link in such a way that it stays generic during the entire process, then all we've done is a planar isotopy, and we haven't changed the pattern of crossings. Recall that there were 3 conditions required to make a link diagram generic. No cusps, and that includes no vertical strands, no intersecting parallel strands, and no crossings with 3 or more ropes involved. To change the pattern of crossings, you must violate one of those 3 conditions. Otherwise, the diagram remains generic and no changes can occur.
The first Reidemeister move, called Reidemeister 1, involves a violation of the no cusps or vertical strands criterion. A strand with a cusp can either form a little loop with 1 crossing, or be smoothed out to have no crossings. A similar thing happens if part of a strand is vertical. It can be flattened out to have a single crossing, or flattened out so it has no crossings. Reidemeister 1 lets us move between the 2 possibilities, either adding or removing a little loop or twist in part of the rope. Reidemeister 2 involves a violation of the no intersecting parallel strands condition. This situation can be made generic either by forming 2 simple crossings, like this, or eliminating the intersection, like this. Reidemeister 2 moves us between the 2 possibilities, sliding a strand over or under another strand to create or eliminate 2 crossings.
Bro, that looks sus.
Bro, shut up! Finally, Reidemeister 3 involves a violation of the condition restricting crossings to at most 2 strands. When 3 strands overlap at a point, we can make a slight adjustment to any one of the 3 strands to create 3 simple crossings. Reidemeister 3 lets us move between the different possibilities. In summary, there are 3 different Reidemeister moves, corresponding to each of the 3 ways a link diagram can fail to be generic. The Reidemeister moves characterize the ways in which an ambient isotopy can change the pattern of crossings of a generic link diagram. All other changes to a link diagram are attained by planar isotopies.
To get a feel for how the Reidemeister moves work, let's write down a sequence of Reidemeister moves we could use to untangle this unknot. I'll abbreviate the names of the moves as R1, R2, and R3. We start with R3 right here, then 2 applications of R2. We adjust things with a planar isotopy and apply R1. After another R2 move, we're nearly there. Just 3 more R1 moves to untwist and get us back to a circle.
That is not a circle, what are you talking about?
It's close enough.
We now have a straightforward understanding of how arbitrary ambient isotopies can change a picture of a link. Every ambient isotopy can be thought of as a sequence of Reidemeister moves, interspersed with planar isotopies. The result is known as Reidemeister's theorem. Crucially, Reidemeister's theorem gives us a clean way of proving a certain quantity is a link invariant. All we have to do is show that the quantity is preserved under planar isotopy and the 3 Reidemeister moves. For example, let's take another look at the linking number. I stated earlier without proof that the linking number of an oriented link doesn't change under any ambient isotopy. We can now prove this fact simply by showing that Reidemeister moves don't change the linking number.
Take Reidemeister 1. It creates or eliminates a crossing, but the overstrand and understrand of that crossing are part of the same link component. Thus, when we compute the linking number, that crossing is assigned the number 0, and its presence or absence has no effect on the sum. Now look at Reidemeister 2. It creates or eliminates 2 crossings. If the 2 strands involved are part of the same component, then both crossings get the number 0. Otherwise, one of the crossings gets the number 1, and the other gets -1. In either case, the sum of the numbers at the 2 crossings is 0, so the presence or absence of the crossings has no effect on the linking number. Finally, for Reidemeister 3, there are 3 oriented strands involved. Let's call them A, B, and C, and 3 crossings, the AB intersection, the BC intersection, and the AC intersection. After Reidemeister 3 is performed, we still have the same 3 intersections. And they're all assigned the same numbers as before because the rope orientations didn't change. Thus, the linking number didn't change. Hence, none of the Reidemeister moves changed the linking number. Since every ambient isotopy can be thought of as a sequence of planar isotopies interspersed with Reidemeister moves, the linking number doesn't change under any ambient isotopy.
Well, Sawyer, what do you think? Are we finally ready to prove why you can't untie your knot?
I sure hope so. All this talk about knots is making me want to tie you up in knots.
Bro, that was not in the script. We're cutting that out. Given a generic link diagram, we want to associate a number with it which is unchanged under ambient isotopies. To do that, it needs to be unchanged under planar isotopies and the 3 Reidemeister moves. We'll use this bracket notation to refer to the quantity associated with a diagram. which we'll call the bracket of the diagram. Remember that if we want the bracket to be unchanged under planar isotopies, it's a good idea to define it solely in terms of the pattern of crossings in the diagram, similar to how the linking number was defined. However, the linking number was too simple. It only depended on the number of crossings and the sign of each crossing, and it didn't take into account more complicated information about how all the crossings were connected to each other. For our new invariant, we will want to somehow take this information into account.
When you're trying to define a complicated quantity, rather than define it directly, one idea is to define it indirectly using a recursive definition. You've probably seen recursive definitions before. They're used when it's easier to define something in terms of smaller instances of itself rather than directly. The most famous example is the Fibonacci numbers, the sequence that starts 1, 1, and then each successive term is the sum of the two previous terms. This definition is recursive because the nth Fibonacci number is not defined directly. Instead, it's defined in terms of smaller instances of itself, namely the previous two Fibonacci numbers. Keep in mind that the Fibonacci numbers are just one example out of many different possibilities. For instance, we could have started the sequence differently, then used the same rule to generate subsequent terms to get this completely different sequence. Or, instead of simply adding the previous two terms, we could multiply each of them by a different number and then add them. There are, of course, many other possibilities.
Let's try to use a recursive definition to define the bracket of a link. Instead of directly saying what the bracket is, we'll define it recursively in terms of smaller or simpler instances of itself. What's a simpler version of this link? Since we should only be caring about the pattern of crossings in the diagram, one idea for simplifying would be to reduce the number of crossings. So let's zoom in on one of the crossings. Since this is a generic link diagram, a crossing consists of two non-parallel strands, the overstrand and the understrand, intersecting at a single point. To eliminate this crossing without changing anything else about the larger diagram, we could do some link surgery and have the strands connect up like this instead, or like this. Zooming out, this means we could make two modified link diagrams that look entirely like the original one, except in one small region where a crossing was removed.
Okay, let's take a step back here because that was a lot to digest. We have a link diagram, which we want to recursively define an invariant for. To do so, we need to create simpler versions of the diagram. And since all we care about is the pattern of crossings, a simpler diagram would be one with fewer crossings. So, we focus in on one of the crossings and get rid of it. There are two sensible ways to do that, resulting in these two diagrams, which are considered simpler versions of the original. Now here's where the recursive part comes in. Similar to how the Fibonacci numbers are defined, the bracket of the original link will be the sum of the brackets of the two simpler links. Well, not quite. If we use this equation exactly, it turns out that we'd get a pretty useless invariant. For the sake of time, we won't go through those details. To get a more useful invariant, we can add more flexibility into the definition, like so. Instead of simply adding the two brackets together, we'll first multiply each by a different fixed number and then add. This is called a skein relation.
Note that this skein relation only involves a single crossing, and it should hold regardless of what the rest of the link is doing. Thus, for notational convenience, we can ignore whatever else is going on and just draw the changes happening to the one crossing. These partial diagrams should be interpreted as complete link diagrams, which are the same outside the region pictured. Now, we still need to determine what the numbers a and b should be. We have some freedom here, but they can't just be anything. We need to pick them in such a way that the bracket of the link is actually an invariant. More specifically, the bracket needs to be unchanged under the three Reidemeister moves. Let's look closely at Reidemeister 2. These two links must have the same bracket because they differ only by a Reidemeister 2 move. Again, assume that any part of the link not shown is the same across both diagrams. What happens when we apply our skein relation to get rid of the two crossings, rather than perform a Reidemeister move? Well, first tackling the top crossing, we get a times this picture plus b times this picture. We have to be careful which picture gets the a and which gets the b. Looking back at the skein relation, we see that when the crossing is oriented so that the overstrand has positive slope, the a is attached to the picture in which the strands connect vertically, whereas the b is attached to the horizontally connected picture. If we rotate the entire link 90 degrees so that now the overstrand has negative slope, the a is attached to the horizontally connected picture and the b to the vertically connected picture. This is consistent with what we did.
Now let's do the bottom crossing. This picture splits into two, with an a here and a b here. And similarly, this one splits with an a here and a b here. At this point, we've gotten rid of both crossings, and we have a sum of 4 terms. We can simplify things a little using a planar isotopy to smooth out the diagrams and combine like terms. Now, the question is, what values of a and b would make this equation true? Well, if these two terms canceled each other out, and a times b were 1, we'd have it. So let's substitute a inverse for b. Now these two terms cancel, and after one more rearrangement, we get that the bracket of this link has to be negative a squared minus a to the minus 2 times the bracket of this link. But the two links differ only by this one extra circle, which doesn't intersect the rest of the link. So this equation is basically telling us another rule that the bracket has to satisfy. Whenever you have a closed loop that doesn't intersect the rest of the link in any way, you can remove it as long as you multiply by a factor of negative a squared minus a to the minus 2. That handles Reidemeister 2. To summarize, we have two skein relations so far. Our original one, using a inverse for b, and this new one, that tells you can remove a loop and multiply by negative a squared minus a to the minus 2. We still have freedom in what a is.
Now, let's ensure the bracket is unchanged under the other Reidemeister moves. Take a look at a Reidemeister 3 situation, where we want to pass a strand over a crossing. Using our first skein relation, we can remove the bottom crossing to get this equation. In this diagram, we can slide the strand simply using a planar isotopy. For this diagram, we already know the bracket is unchanged if we do Reidemeister 2 moves, so we're allowed to slide the strand like this, doing 2 Reidemeister 2 moves. Now we can recreate the crossing we destroyed, using the skein relation in reverse. The conclusion is that the bracket of the original link is the same as the bracket of the link once a type 3 Reidemeister move has been applied, so we don't need any additional constraints. Type 3 Reidemeister moves already are guaranteed to preserve the bracket.
Last but not least, we need to investigate Reidemeister 1 moves. Take a little loop and use our skein relation to eliminate the crossing. In the right diagram, we can get rid of the extra loop by multiplying by negative a squared minus a to the minus 2. Now after straightening things out, we can simplify and combine like terms to get this. There are two ways to proceed from here. The first way assumes that the bracket, as we've already defined it, is invariant under type 1 Reidemeister moves. So the left-hand side untwists, and minus a to the minus 3 has to be 1. Hence, a can be any of the three complex roots of negative 1, which are negative 1, e to the I pi over 3, and e to the negative I pi over 3. This gives us a valid link invariant.
But we're going to focus on the second way, because it leads to a better invariant. We'll leave the troublesome factor of minus a to the minus 3 there for now, and do something to cancel it out at the very end. What do I mean by that exactly? Well, suppose we take a big complicated picture of a link, and we use the two skein relations to calculate its bracket, systematically eliminating all crossings and the loops that form when those crossings are removed. By the end of the procedure, we'll end up with some expression in terms of a. This isn't an invariant yet, because if we had started with extra twists, we would have ended with extra factors of minus a to the minus 3, according to this equation. The sensible thing to do would be to count all the twists in the original link and multiply by minus a cubed for each of them to cancel out the minus a to the minus 3. Doing that would make it invariant. This almost works, except the crossings which came from a twist might not be so obviously distinguishable from the other crossings. For instance, we could do some Reidemeister 2 and 3 moves here to bury this twist in the middle. Now this crossing is not obviously part of a twist, but it still should count for a factor of minus a cubed. So it seems that the resolution to all of our woes would be to look at every crossing in the original diagram and have it count for a factor of minus a cubed. Well, we don't have to look at every crossing, just the ones where the overstrand and understrand come from the same link component, since when they don't, that crossing couldn't have possibly come from a twist. The factors of minus a cubed we'll call the canceling factors, since they're meant to cancel the unwanted factors of minus a to the minus 3 generated by Reidemeister 1 moves. There's one more slight issue to address, which is that if the twist was like this instead, we would have ended up with minus a cubed. So the canceling factor for this crossing should be minus a to the minus 3. There's an easy way to distinguish the two cases. Start by introducing an orientation on the link, like we did before when calculating the linking number. If, when you rotate the overstrand counterclockwise to match the understrand, the orientations align, then the unwanted factor is minus a cubed, and the canceling factor is minus a to the minus 3. On the other hand, if the orientations don't align, it's the other way around.
Now we finally have a true link invariant. To compute it, you start by calculating the link's bracket polynomial, using Rule 1, which tells us how to eliminate crossings, Rule 2, which tells us how to vanquish loops, and Rule 3, which tells us how to neutralize twists. Once you're done calculating the bracket, go back to the original picture and figure out what canceling factors you need by looking at every crossing where the overstrand and understrand come from the same link component and determining whether you should multiply by -a cubed or -a to the -3. The resulting expression in terms of a, with canceling factors included, we'll call the x of the link. It's invariant under planar isotopies because both the bracket and the canceling factors only depend on the pattern of crossings. It's invariant under type 1 Reidemeister moves, since although the bracket changes when a type 1 move is performed, the canceling factors are there to automatically neutralize that change. It's invariant under type 2 Reidemeister moves because the bracket doesn't change, and the two canceling factors generated or removed by a type 2 move always cancel each other out. Lastly, it's invariant under type 3 Reidemeister moves because the bracket doesn't change, and the canceling factors don't change either. Thus, the x of a link is invariant under all ambient isotopies, and it doesn't even matter what a is. Since a can be anything, conventionally it's just left as a variable. This means the invariant we have isn't a numeric invariant, but rather a polynomial invariant, so we call it the x polynomial.
Alright, time to finally do an example and see the x polynomial in action. Let's go back to the knot we saw at the very beginning of the video, called the trefoil, which we couldn't untangle. We'll compute the x of this knot by first computing the bracket polynomial using the skein relations for crossings, loops, and twists, then applying canceling factors at the end. Let's start by applying Rule 1 to the bottom crossing to get these two terms. For the left term, we'll use Rule 3 to remove the twists. We just need to check the orientation of the crossing, which in both cases brings out a factor of -a cubed. Now let's look at the right term, and apply Rule 1 again on this crossing here. That gives us these two terms. And we're once again able to use Rule 3 as we untwist them into loops. Looking at the orientation, the left term contributes a factor of -a cubed, and the right term includes -a to the -3. From here, we'll factor out the loop. Then apply Rule 2 to get the entire polynomial in terms of a. This finally gives us the bracket polynomial of the trefoil, so we're almost done. We just need to multiply by the canceling factors, as per Rule 4, by going back to the original diagram and checking every crossing between strands from the same component, which is all of them since this is a knot. There are 3 crossings, and each contributes an extra -a cubed, which gives us an extra -a to the 9 factor on top of everything. And with that, we've got our link invariant. Let's go!
Bro, calm down.
Since the x polynomial of a link is invariant under ambient isotopy, no matter how we manipulate the trefoil, if we were to recompute the x polynomial, we'd get the exact same thing. That's a rigorous proof you can't untangle it, no matter what, because the x polynomial of the unknot is -a squared -a to the -2, which is different. Our definition of the x polynomial is a little bit unconventional, but if you've done any knot theory before, you may have heard of the Jones polynomial, which is probably the most famous link invariant, and it's very closely related to our x polynomial. It was discovered by mathematician Vaughan Jones in 1984, who later won the Fields Medal in 1990 for his work surrounding the discovery. To get from the x polynomial to the Jones polynomial, you first divide by -a squared -a to the -2, then multiply by a to the -6 times the linking number, then replace every a with t to the -4th to get a polynomial in T. These steps don't change the fact that the quantity is an invariant, since if you remember from earlier, the linking number is also an invariant. The result is the Jones polynomial of the link, denoted with a v. The x polynomial and the Jones polynomial are more or less interchangeable, so we'll stick to using the Jones polynomial since that's the more conventional invariant.
Here's another interesting application. There are actually 2 different versions of the trefoil, the right-handed trefoil and the left-handed. We computed the Jones polynomial of the left-handed version. If you did the same for the right-handed, you'd get this instead. These 2 polynomials are not the same, which means the right-handed and left-handed trefoil really are different. There's no way to transform one to look exactly like the other, even though they look nearly identical.
One important question is the question of whether or not the Jones polynomial can distinguish any 2 distinct knots. This is unfortunately not the case. For instance, it's known that these two knots are distinct, but their Jones polynomials are equal. So, while the Jones polynomial is quite powerful, it's not the end-all for knot invariance.
What about distinguishing knots from the unknot? If a knot has a Jones polynomial that isn't 1, then that knot certainly isn't the unknot, since the unknot has Jones polynomial 1. But if the Jones polynomial is 1, it's possible that the knot is the unknot, and it's possible that it isn't. Thus far, no one has ever found a non-trivial knot that has Jones polynomial 1, but no one has proven that it doesn't exist. It's an open question in knot theory. There's a lot more we could say about the Jones polynomial and other knot theory stuff in general, but we'll save that for another time. But if you want to mess around with more knots and links in your own spare time, there's this website called knotful.io that lets you draw your own links and find their Jones polynomial and other link invariants. It's a really great resource if you're interested in the topic. And really, knot theory is super vast and kind of underrated, so I would highly recommend looking more into it if I already said that.
As usual, we left some practice problems on screen, so if you're keen to try out the ideas from this video for yourself, you can go ahead and give those problems a shot. Other than that, just next time you find yourself with a collection of tangled up loops and you don't know how to untie it, just remember the Jones polynomial. You might be trying to do the impossible.
Mine's not impossible. I did great. You didn't even finish.
Bro.
Oh.